Founders. My name is Carlos Lara, AI Technical Founder, and today we will continue building our neural network from scratch with PyTorch. In the previous tutorial, we learned how to build our neural network from scratch using only torch.tensor, the PyTorch tensor, the most fundamental class, and using the built-in Python functions using pure Python. So after having done that, as you can see, this is the last that we did. Here's a small training of a linear model. The next step is we're going to start using the beautiful PyTorch modules and classes to start refactoring and cleaning up our code, our model that we created by hand, and start seeing how PyTorch comes together very nicely and emerges very naturally from just regular Python. So the first step we're going to do is we will refactor our code using torch_nn.functional. And this module contains all of the functions in the torch_nn library. So it contains a wide range of loss and activation functions, and also convenient functions for creating neural networks like pooling functions and so on. So since we're using log likelihood, loss, and log softmax activation and the previous tutorial here, we're now going to use PyTorch, and we're going to use a single function here that combines those two functions, the loss and the activation function, which is cross entropy, the cross entropy function, which so we usually import it as torch_nn.functional as f. So we're going to pull that cross entropy loss function from f here. So we are going to assign a variable loss function, and now it's going to be our cross entropy function here from f, from torch_nn functional. And now for our model, we're going to have this this is what we had before, which is our model takes in our input and just calculates this. So a dot product with the weights and then adds the bias. So now that we're no longer calling log softmax in the model function, we can just pass in this directly here, and we have our loss, because that's going to take care of those two. And feel free to pause and just make sure that everything makes sense. So let's go ahead and run this. So now our loss is the same as before. So this is the same. It's just being refactored. Now we're using the PyTorch modules and classes. So now we're going to refactor using nn.module, and torch_nn module is the base class for all neural network modules. So your models should subclass this class right here. And nn.parameter is a kind of a tensor that is to be considered a module parameter. So nn.parameter instances are tensor subclasses, torch tensor subclasses that have a very special property that when used with modules, when they're assigned as module attributes, they are automatically added to the list of its parameters. And you can access that through the parameters iterator. So we're going to be refactoring using those two and cleaning up our loop here. So it's an abstract class. So we're going to have to provide an implementation for an nn.module, as we'll see in a moment. So here first, we're going to create our MNIST logistic. It's our class that's going to inherit from an nn.module. As we said, we always inherit from that. So we define our constructor here, our init function, and then as always, when creating a class, we'll just call the base class or the super class here and initialize that. So now for weights, instead of assigning them as global variables as we had before, now they are attributes here of our nn.module subclass, in this case, MNIST logistic. So we're going to assign self.weight, self.bias, and then we're going to wrap our tensors in an nn.parameter here. So nn.parameter, and then we pass in our tensor, just as before for our linear layer, 784 inputs in the input layer, leading out to 10 to an input layer, to an output layer of 10, corresponding to the classification for our MNIST digits. And then again, Xavier initialization for our weights. And same for the bias. So we're just wrapping our tensors in our nn.dot parameter, so we can just access them here. So you see, it's very concise now how we're putting everything here together instead of having individual parts. Now with PyTorch, with our classes here, module and parameter, we can just put it in one place, and it's just very easy to see, more readable and more convenient. So, and as I said before, an nn.module has a number of attributes and methods such as .parameters and .0grad, which we will be using. And we have a forward method. So for the feed forward pass of our model, we're going to return this now. It's our inputs.product with the weights and adding the bias. Everything's put together. Now, an instance of our class here, so we're going to create an instance of our class. So our model, we're going to assign an MNIST logistics. So we're just constructing it here. So we have that. And now, to call our forward function, so when we pass our inputs, in this case, where XB, we're passing our inputs into the model, we don't have to say model.forward. So our model we can just call the model itself passing the input, and it will automatically, PyTorch will know to call this forward function, to pass the input into the forward function. So we'll go ahead and do that. So NN.module objects are used as if they are functions, they are callable. And as I said, behind the scenes, PyTorch will call that forward method automatically. So there we go. So now, previously for our training loop, we had to update the values for each parameter by name and manually zero out the gradients for each parameter separately. So now we can take advantage of model.parameters and model.zeroGrad functions, which are both defined by PyTorch, to make those steps more concise and less prone to error. Error, for example, you can forget some of the parameters. And for example, if you have a more complicated model, a lot of other parameters, that's just more prone to error if you're doing it manually like that. So that's where PyTorch comes in and gives us more convenience methods and functions here that we can use. So we're going to wrap our training loop in a fit function, so we can run it again later. We don't have to rewrite it every time. We just wrap it into a function here, a fit function, and we're doing the same as we were doing before, as you can see. And we'll start replacing parts of this with our new a new way of doing it. So again, we're just looping our epochs, our batches, indexing here, our X and train, prediction model. It's just the same as before. But see here, for iteration here, we can just say for P and model.parameters, and we apply this. This is how we update our parameters. So it's already giving us a value here by having refactored it. And then model.zeroGrad, instead of zeroing out as we had before by hand, as you see, each weights and bias here, tensor.grad.0 in place, and updating here by hand. Now it's just much more convenient here with these model.parameters, model.zeroGrad. So very nice. And we call our fit function. Now here we can double check, and our loss has indeed gone down. So same behavior as before, it's just nice, cleaner, more refactor, more convenient. So now the next step is we're going to refactor using nn.linear, and that's for our linear layer. So instead of manually defining and initializing self.weights and self.bias as we did before, which was already adding value and calculating that dot product and adding the bias, or that matrix multiplication, we will use the PyTorch class nn.linear for a linear layer, which will do all of that for us, which is very nice. So PyTorch has many types of predefined layers that can greatly simplify our code, and often making it faster too. And we have other layers like convolutional layers, max pooling layers, and so on. So here we have our class again, but instead of initializing the weights and the bias as before, as we had here with an nn.parameter, we just simply initialize a linear layer, which will take care of that, of the weights and the bias for us. Now, for Xavier initialization, or for some weight initialization, you're going to have to take care of that, because it's automatically created without any kind of special weight initialization, just random as before. So we do self.lin, and when we construct here our module, as usual, we call our superclass. And that's it. That's all we need to do. In our forward method, we just pass in our input tensor here and into the linear layer itself. So very nice, cleaner, it's easier to see, cleaner code. Again, with PyTorch. And now we're going to do the same thing now, but we instantiate our model and use the fit function as before. And again, feel free to pause and make sure that everything makes sense here. So we can now further clean up and refactor our code now using Torch and then a Torch Optim here, which is a package that contains various optimization algorithms. So for example, it contains gradient descent optimizers and here. So we can use a step method from our optimizer that comes in there to take a forward step, which will take care of us this process of updating the parameters instead of us how we were doing manually updating it. Even this looping through for p and model.parameters, it's nice, but what if we can do that in just one step, one line of code, just doing a gradient descent step in our optimizer? And that's what we're going to do here. So we import optim from Torch. Now we define our get model here. It's a little function that's going to create our model and optimizer in one step. And sure, this is not adhering to the single responsibility principle of object-oriented programming, but here, just to make the point and understand it's okay right now. So this get model is going to return a model, an instance, as before, and it's also going to return optim.sgd. SGD stands for a stochastic gradient descent. So it's a gradient descent optimizer that is an optim here. And we're going to pass in two parameters. So the parameters of our model, so we have model that we just created dot parameters. And again, just by the fact that we created it using PyTorch modules, here we can just access the parameters just like that. It's very nice and convenient. And then pass in a hyperparameter here, the learning rate. And for the learning rate, as we have before, we just assigned it here. We defined it previously. So we pass those two parameters here to our stochastic gradient descent from optim, and this is just a convenience function that returns both the model and the gradient descent optimizer. So we store that on those in variables here, and here we can just do the same loop as before. Let me just make some space here so you can see a little bit better what's going on. So the same as before, but now here when we do our backward here, our back propagation here for our loss, now we just call optimizer, right? Our gradient descent optimizer dot step. So we do the step and then we do 0 grad. So those two steps take care of what we were doing before here. So it's just nicer, just easier and cleaner. And look, now we don't need to say with torch dot no grad as before, because we don't want that those steps here, updating the parameters, that itself recorded in the dynamic computational graph. But the optimizer here, when we call optimizer or op.step, it already does it like that. So again, just less code, simpler, easier to see, and using PyTorch here, using our optim, torch.optim module. So now we're going to refactor using datasets, our data. So PyTorch has an abstract dataset class, which means that you must provide an implementation for it. You must, if you want to create an instance, you must subclass it, you must inherit from dataset, and you must provide an implementation for these abstract methods here, which is the length. So it's a function that returns the length of our dataset, and then get item function as a way of indexing into our dataset. So PyTorch tensor dataset is a dataset that wraps tensors. So we're going to define a length, and as we said, a way of indexing with get item, to be able to iterate, index, and slice along the first dimension of a tensor. So let's go ahead and bring that in. So import tensor dataset from torch.utils.data. And now we're going to combine our X train and Y train, so our features and our labels, into a single tensor dataset class that is inheriting from the dataset abstract class. So we're just going to assign that in one variable here and pass those two as parameters. So again, it's already it's cleaning up better the code. It's less code. It's easier to see, more concise, and providing more functionality. It's easier to extend as well. So before we were iterating through many batches of X and Y values, so features and labels separately, and indexing as you saw before, but now we can do that in a much better way here. So here we create an instance of our tensor dataset here, our train dataset, and now here we just index it directly here as we loop. So again, we pass it into our model, which calls our forward function. PyTorch will call forward function behind the scenes. Get our loss, same as before. Remember, our loss is our cross entropy loss. Loss.backward, do the back propagation here, and then optimizer. So just everything is just clean and concise. And we just print that out. So here, the last thing that we're going to do is we're going to refactor using data loader. So PyTorch data loader is responsible for managing batches. So you can create a data loader from any data set. In this case, our tensor dataset class. So data loader will make it easy to iterate over batches. So rather than having to index our trained data set like this, the data loader will give us a mini batch automatically. So again, just our code just keeps getting cleaner, more convenient, and just easier to extend. So as you see, PyTorch provides all these beautiful classes and functions to make your code very nice, very readable, very extensible, and very, very nice and easy to maintain and to read. Also for developers or engineers coming into PyTorch, it's just very easy and very intuitive to see what's going on and how everything is fitting together. So we create our train data set here as before, and now our train data loader. So for our data loader, we just import it from torch.utils.data, and then when we create an instance here and assign it to a variable, we're going to pass in the train data set that we just created and the batch size, which is another hyperparameter that you can tune. So we patch our batch size. And now, so previously our loop iterated over the batches and indexing. So now look at what we get at the end here, or at this stage. Just a very nice, so we're going, just concise code here. As before, we have our get model convenience function that returns our model and our gradient descent optimizer. We loop through our epochs, and epochs is another hyperparameter here that we chose. And so again, our model, so we have hyperparameters, and our model is the learnable parameters is what it's updating. This gradient descent optimizer is updating our learning and updating our learnable parameters, but we ourselves set the hyperparameters. So we're iterating here. So for XB and YB in the train data loader, so for our data loader, we can just loop through it, iterate through it just like that, just for the features and labels in the train data loader. Very convenient. We're just going to pass in the features to our model, forward, again, PyTorch behind the scenes calling forward here for our model instance that we created. Using so nn.module again, right? So we have our output, our prediction, and then we compare with the actual labels that are right here using our cross entropy loss function. Backpropagate that loss.backward, and then just do our gradient descent step that updates our weights, zero out the gradient to prepare for the next iteration, and we print that out, and that's it. So that's what we had. So thanks to PyTorch's nn.module, nn.parameter, dataset, data loader, and nn.optim for gradient descent optimizers, our training loop is now dramatically smaller, easier to understand. And so the next step will be to add basic features necessary to create effective models in practice, such as validation here and so on. So we'll continue from here. So thank you for watching. If you have any questions, thoughts, comment below, or also if there's something in particular that you'd like me to cover, a specific topic here with PyTorch or with deep learning, also let me know in the comments, and I will see you next time.